This video provides a technical overview of fiber optic network design and topology, highlighting the advantages of a structured three-layer model: access, distribution, core. It explains each layer's role through real-world examples such as urban power grids, milk production chains, and university networks, emphasizing best practices and compliance with FOA, IEEE, and TIA standards. A well-structured fiber optic network forms the backbone of modern high-speed communication. The three-layer hierarchical network model: access, distribution, and core provides the essential framework for design, deployment, and management. Its modular structure simplifies troubleshooting and ensures reliable scalability to meet growing bandwidth demands. The access, distribution, and core layers form a hierarchical system. Data flows upward from end devices through the access layer, aggregated and processed by the distribution layer, and delivered across high-speed backbones in the core. Control and redundancy flow downward, ensuring stability, scalability, and efficient management across all tiers. The access layer forms the network's physical edge, directly connecting end devices, sensors, or entry points. It enables immediate user access to the main fiber network through methods like PON or fiber.esc links. Key traits include high port density, lower total bandwidth than upper layers, and use of simple, cost-effective optical components such as splitters. The distribution layer serves as the key intermediary, aggregating traffic from multiple access layer switches. It enforces network policies, manages routing, applies costs, and implements ACLs for security. This layer forms the boundary between local access domains and the core, offering redundancy and higher forwarding speed than the access layer. The distribution layer serves as the key intermediary, aggregating traffic from multiple access layer switches. It enforces network policies, manages routing, applies costs, and implements ACLs for security. This layer forms the boundary between local access domains and the core, offering redundancy and higher forwarding speed than the access layer. Adopting this structured methodology yields substantial operational and architectural benefits. The network's modular design supports seamless scalability. New access segments can be integrated without altering the core architecture, ensuring expansion with minimal disruption. Capacity upgrades occur only within the layer that requires enhancement, preserving stability and cost efficiency while allowing future growth. The structured network architecture enhances manageability by isolating issues within specific layers. Faults can be quickly identified and corrected without affecting the entire topology, drastically reducing mean time to repair enter. Each layer's defined role simplifies monitoring, maintenance, and long-term operational control. Network performance is optimized by enforcing traffic policies at the distribution layer, ensuring smooth data flow and preventing congestion within the high-speed core. This separation of control and transit maintains low latency, high throughput, and consistent response times across all segments of the infrastructure. Network resilience is achieved through redundant links and diverse physical paths carefully designed for each layer. This multi-layer redundancy ensures fault tolerance and rapid recovery from failures, maintaining continuous connectivity, even under adverse conditions while minimizing service interruption across the entire infrastructure. The three-layer topology is not exclusive to ID networking. It is an optimal organization structure used across various complex, large-scale systems where segmented reliability and scalable growth are paramount. Modern electrical grids reflect the three-layer model. Access: low-voltage lines supply homes and small businesses. Distribution: substations balance regional loads and protect circuits like routers. Core: high-voltage lines link generation plants and substations, forming the resilient backbone of power delivery. The milk supply chain follows a three-layer model. Farms produce raw milk: access, Regional plants process and manage quality distribution, and national cold hubs handle large-scale transport while maintaining the cold chain core. A large university network follows a three-layer model: fiber links to devices and Wi-Fi access, building switches handling routing and security distribution, and a redundant campus backbone with high-speed fiber rings connecting all buildings to data centers and internet core. Fiber choice depends on distance, speed, and cost. SEMF9M suits long-range links like WANs and campus backbones using 131015550nm wavelengths, offering minimal dispersion. MF5062 5M fits short in-building runs up to 150M, supports 100G speeds, and is cheaper but limited by higher modal dispersion. Fiber choice depends on distance, speed, and cost. SEMF9M suits long-range links like WANs and campus backbones using 131015550nm wavelengths, offering minimal dispersion. MF5062 5M fits short in-building runs up to 150M, supports 100G speeds, and is cheaper but limited by higher modal dispersion. Connector choice affects performance and density. LC125 dominates modern systems for SF or SF plus ports and access or distribution layers. SC25 is legacy but used in some PON setups. MPO or ME-TP824 fiber ferrule supports high-speed parallel optics 40G100G and dense distribution and core networks, ensuring efficient fiber management and reliability. Network resilience depends on topology. STAR connects nodes to a single hub, easy management but vulnerable to hub failure. Ring forms a closed loop, ensuring rerouting if one link fails, common in SONET or SDH and ERP systems. Mesh interlinks all nodes, delivering maximum redundancy and uptime for core networks but with higher cost and complexity. Global standards guarantee interoperability and reliability. FOA oversees installation or testing. IE 802.3 defines data protocols, TIA 568 structures building cabling, and ITIG 694 governs DDUM and carry air-grade optical transport. Fiber testing ensures design compliance. OTDR pinpoints faults and measures attenuation along the link. OPM or OLTS verify end-to-end power loss against allowed thresholds. OT 35 dB splices plus OT 75 dB connectors plus OT 25 dB km distance. FEL uses visible red light to trace fibers and detect breaks or bends, allowing rapid field diagnostics and certification. A structured three-layer design: access, distribution, core combined with strict FOA or E compliance and precise testing creates scalable, manageable, and high-performance fiber infrastructures. This disciplined approach delivers resilient, future-proof networks ready to meet growing bandwidth demands of modern ecosystems.